Alrighty, everybody. So welcome to the last unit of AP Chemistry. It is Unit 14, Electrochemistry. Now, before we get started, I do want to give you a heads up that this unit is very heavily centered around oxidation-reduction reactions, also known as redox reactions. If you forgot what redox is, you might want to look at it more in detail from Unit 4, where we looked at aqueous reactions. But we're going to do a very brief review right here, and then we're going to get into the actual electrochemistry because it's pretty much all dependent on this type of reaction. Okay, so reduction reactions are very simple. It's reactions where electrons move from one reactant to another. So when you have a chemical reaction, it's basically looking at how electrons move from one compound to another compound. The acronym you want to know is oil rig. Oxidation is loss. So if an element loses electrons, it is oxidized. Reduction is gain. If an element gains electrons, it is called reduced. Okay, now we look at oxidation reduction and how electrons move through a system called oxidation numbers. So this is the list right here. We're going to go through it very briefly, but again, if you want a more detailed explanation for each of these, you might want to go back to Unit 4 and look at redox numbers. So first rule is that any atom in its elemental form, so its most basic form in nature, has an oxidation number of 0. So for example, hydrogen, H2, diatomic gas is going to be its elemental form. Other examples of diatomic gases are things like nitrogen, oxygen, fluorine, chlorine, so on and so forth. These gases, they are in their elemental form when they are diatomic gases. So when you have two of the elements bonded together. Each of the elements will have an oxidation number of 0. The other important thing to know is that most metals have an oxidation number of 0 when they are in their solid form. So calcium, when it's solid, is going to have an oxidation number of 0. Another example might be like sodium. When it's a solid, it's going to have an oxidation number of 0. Next rule, monatomic ions, their oxidation number are equal to their ionic charge. So for example, K right here has a charge of +1. Oxidation number will be +1. Sulfur right here has a charge of -2. Oxidation number will be -2. When they're monatomic ions, it's really, really easy. All right, the other one you need to know is that the big oxidation number rule that you need to know is that oxygen 99.9% of the time will be -2, and this is the one that's going to actually drive most of the oxidation numbers. So if you have a compound, for example, like SO3, we're gonna look at oxygen and say that, hey, there are 3 oxygens. We know that oxygen is typically -2 oxidation number, and there are 3 of them. S is balancing out the 3 here, so that means S has to be +6. Okay? So that's 99% of the time. The only exception is when you have a peroxide ion, O2 2-, and in that situation, each oxygen has a oxidation number of -1. Okay, and this is the one that's typically that you're going to need to know for most of them. There are other rules that you can take a look at. I'm not going to talk about them here because oxygen is the one that usually drives everything. All right, one other thing I do want to mention is that when you have a polyatomic ion, so like SO4 2-, sulfate, and again, this is why you want to memorize your polyatomic ions. If you look at sulfate right here, you see how the polyatomic ion has a charge of -2, right? That means that when you add up the oxidation numbers of everything in that polyatomic ion, it's going to add up to -2. And we're going to use oxygen as the base for the oxidation number. So if you take a look right here, so there are 4 oxygens. We know that each oxygen should be -2 because it's not peroxide. And 1 sulfur is going to, when you combine 1 sulfur with all these oxygens, you should get -2. That means sulfur has to be +6 because +6 plus -8 is going to give you -2. So that's another way you can find the oxidation numbers of each individual element, which is described more in detail right here. All right, so we just took a look at this right here, so we're going to move on. If you want to try this one out, you can. So pause the video. I will give you the answer. Pause the video, try it out. We just took a look at sulfate, but see if you can figure out the oxidation number of each element in this compound. So pause the video right here and try it out. All right, so welcome back. So we said that oxygen has to be -2. So -2, and there's 4 of them. And we're going to take a look at this compound. We saw earlier that SO4 is sulfate, right? SO4 2-. That means that S plus the 4 oxygens have to equal -2, which means that S right here has to be +6. Well, we know that there are 2 H's right here, and if you look at this entire molecule, it is neutral. Sulfate has -2, but when they're all combined, it balances out. That means that the 2 hydrogens need to balance out the -2. So it'll be +1, +1. And so if you add all of these numbers right here, you will end up with a charge of 0, and this is a neutral molecule, so that works out. All right, so that's how you find oxidation numbers for an individual molecule. But now we're going to look at how different elements get oxidized and reduced in a reaction. So here we have this equation right here, and what you're trying to do is you're trying to figure out which compound is oxidized and which compound is reduced. So if you remember your acronym, oil rig, oxidation is loss and reduction is gain. Oxidation is when you lose electrons, and reduction is when you gain electrons. Now, let's think about this logically, okay? Electrons are negatively charged, right? So if you are losing electrons, you are losing negativity. And if you lose negativity, you become more positive. Okay, just like how when you get out of this class, you will become oxidized because you will lose a negative influence in me, and you will become a more positive person. Okay, on the other hand, reduction is gain. Again, remember, electrons are negative, so if you gain negative things, you will become more negative. So when we are looking at which species is oxidized and reduced, we want to figure out basically which one is becoming more positive and which one is becoming more negative. So first thing we're going to do is we're going to look at the oxidation numbers of each element in this entire equation. So let's start with the reactant side. I'm going to do the reactant side for you, and you'll try the products. Let's start with Mg. If you take a look at Mg, Mg is a metal, and it's by itself. So if it's by itself, that means the oxidation number will be 0. Okay, we have HCl. We should be able to identify that that is an ionic compound. And we know that HCl is made out of a H+, so +1, and chloride, which is -1. Okay, now I want you to pause the video and try the product side. Find the oxidation numbers of each element on the product side. All right, welcome back. So if we take a look at H2, this is the one that should be easiest. This is a diatomic gas, which is the elemental form of hydrogen, so that's going to be 0. If we take a look at Mg right here, MgCl2, we can identify this as an ionic compound. Mg, the most common ion, is +2. And chlorine is going to be -1. Okay, I know there's 2 of them, but each chlorine is -1, so I'm just going to mark -1. All right, so what we're going to do now is we're just going to figure out how each element's oxidation number changed. So if we take a look at this equation, we can see that chlorine did not change, right? Chlorine was -1, and it stayed -1, so this was neither oxidized nor reduced. It just stayed the same. If we take a look at magnesium, though, magnesium went from 0 to +2. So we want to figure out on a number line, did the number go up or did it go down? Did it become more positive or more negative? So magnesium went from 0 and it went to +2. We can see that it moves in the positive direction. So since magnesium became more positive, we can say that this is the one that was oxidized. Okay, so magnesium is oxidized. All right, which means that the other one is the one that is reduced, but let's just double check our answer. If you take a look at hydrogen, hydrogen went from +1 to 0. And if we look at our number line, +1 will be right here. If we go from +1 to 0, we are moving in the negative direction. That means it became more negative. That means that hydrogen was reduced. Okay, so if we were to write this out, we would say magnesium is oxidized and hydrogen is reduced in this reaction. Okay, the key thing that you should notice from here is that oxidation and reduction go hand in hand. You can't have one happen without the other. So if one substance is oxidized, that means in the reaction, another one of the substances has to be reduced. Alrighty. So before we move on, I'm not going to scroll down too much, but at the bottom of the screen, you should see this reaction right here. I want you to pause the video and see if you guys can figure out which of these substances is oxidized and which one is reduced. So pause the video and try that out. Alright, welcome back, guys. Let's go over the oxidation numbers and then we'll figure out which one was oxidized and reduced. If we take a look at Fe, Fe is a metal. It's by itself, so this is its elemental form, so 0 right here. We see another HCl. That means this is going to be positive 1, negative 1. H in its elemental form, H2, the diatomic gas, is 0. And here we have FeCl2. Well, Fe is a transition metal, so we don't always have a most common ion for it. However, we see that it's bonded to chlorine. And chlorine is, the most common ion is negative 1. And there's 2 of them. Negative 1, negative 1. That means Fe has to be plus 2. Okay, so if you take a look, it's very similar to the previous example. You should identify that Fe becomes more positive. That means that Fe here is oxidized. And we can see that hydrogen becomes more negative, so H is reduced. All right, now we identified which one is oxidized and which one's reduced. Now I'm going to show you guys something called a half reaction. Okay, and a half reaction is where we take a chemical equation and we just write the reaction for just what happened in the oxidation and just what happened in the reduction. So if we take a look at this reaction right here, we can see that Fe is oxidized. So let's write the half reaction. So we're going to write the oxidation half reaction. Okay. Now we start with, we're going to take a look at what happens to Fe. Okay. So we can see that Fe is by itself. And remember, oxidation is loss, oil rig. Just remember the acronym, oil rig. Oxidation is loss. Fe loses its electrons. So that means that Fe is going to become Fe2+, and since it lost its electrons, it's going to separate. So electrons are going to be a product. And how many? If it goes from 0 to +2, that means it loses 2 electrons. So when you have an oxidation half reaction, you might want to jot this down. Electrons are products. Okay, because it is separating from the electrons. It's losing them, so electrons are the product. On the other hand, for the reduction half reaction, okay, we can take a look at hydrogen. If you take a look at hydrogen, on the reactant side, it is an ion. It's going to be H+. And how many are there? There's a 2 in the front, so there are 2. And reduction is gaining electrons. So what's happening is this hydrogen is gaining or combining with electrons, so +2 electrons, and it forms H2, which is the form that it has on the product side. So you might want to jot this down as well. In oxidation half reactions, electrons are products. In reduction half reactions, electrons are reactants. Okay, because it is gaining, it is combining with those electrons. A key thing to note is that when you write a half reaction, it needs to be balanced. Okay, so if we took a look at hydrogen right here, we see H. Now let's say I just forgot to put a coefficient 2 right here. Okay, we can see that H on the reactant side is H+, and on the product side is H2. So you want to make sure that you balance it, so you would want to add a 2 there in case you forgot. Okay, but those are the half reactions right here. All right, now half reactions are very important to electrochem, so I want you to pause the video, and I want you to try number 3 on your own. See if you can first identify what is oxidized and what is reduced, and then see if you can write their half reactions. Try that out. All right, welcome back. Let's go over this. Now, this problem is pretty easy because it gives you the charges. There's no neutral thing, so we can just take a look at the charges for the oxidation numbers. This is +1, this is +4, +3, and +2. If we take a look at chromium, Cr, we can see it goes from +1 to +3. That means it becomes more positive. Now, if you remember our acronym oil rig, oxidation is loss and reduction is gain. Losing electrons is losing something negative. If you lose something negative, you become more positive. So if you take a look at chromium, we can see that it became more positive. So that means chromium was oxidized. So for part A, chromium is oxidized. And then for reduction, there's only one other thing in the reaction, which is SN, tin. And that means tin has to be reduced. But we can check our answer. We go from +4 to +2. We became a bit more negative here. So that means that tin is the one that is reduced. Okay, so let's write the half reactions for oxidation and reduction. So let's start with the oxidation half reaction. So we're going to take a look at the compound that was oxidized, which was chromium. If we take a look at the reactant side, chromium was Cr+, and if you look at the product side, it's Cr3+. So we just need to figure out which side the electrons are going to go. Now, if you are oxidized, you are losing electrons. If you lose electrons, that means that you are splitting apart from them. So that means chromium is splitting from the electrons, and to go from +1 to +3, you are splitting from 2 electrons. Remember, oxidation half reaction, electrons are a product. And then for reduction half reactions, we're going to take a look at SN. On the reactant side, SN is 4+. On the product side, it's 2+. And if you are being reduced, you are gaining electrons. You're combining with electrons. So that means that electrons are going to be a reactant. And we went from +4 to +2, so it's going to be 2 electrons. And what you should notice is if we use Hess's law to combine these two reactions, the electrons actually cancel out. And then on the reactant side, you get exactly what's up here. And on the product side, you get exactly what's up here. So Hess's law works for half reactions. So if you're ever in doubt about your half reactions, use Hess's law to combine them, and you should end up with the complete reaction that you have right here. All right, now speaking of Hess's law, this is important because there may be problems on the AP test where you are asked to combine two half reactions to figure out some information about a reaction. So we're going to take a look at a problem right here, 14.4. This is kind of a complicated problem in the sense that there's a lot of text that you need to read, so it might seem a little complex, but it's actually really easy to understand. So let's. I'm going to draw it for you guys so you can visualize it, but let's go through the problem sentence by sentence. First, it says 50 milliliters of sodium oxalate is poured into an Erlenmeyer flask. So basically what's happening here is that you have an Erlenmeyer flask, and somebody is pouring in 50 milliliters of sodium oxalate, and it gives you the formula, Na2C2O4. And then it tells you an acidified solution of 0.135 molarity potassium permanganate is titrated into the flask while the solution is swirled on a stir station and heated. So basically what you are doing is you are adding 0.135 molarity potassium permanganate, and then the solution is stirred and heated basically to make sure the reaction goes to completion and faster. And then it tells you solution is originally colorless but turns pink after 14.65 milliliters of potassium permanganate is added. So basically, if you think back to titration from Unit 12, we know that when there is a color change, that is when you are at equivalence point. Okay, and equivalence point, if you remember, is when you have your base solution, when the moles of the base solution are equal to the moles of the solution added. Okay, and usually we talk about acid equal base, but in this situation we're not looking specifically at an acid and base. So we're just going to look at this. So basically what's happening is the potassium permanganate that you added has reacted fully with the sodium oxalate when you add 14.56 milliliters. And then it gives you the two half reactions. What it's asking you to find is what is the concentration of the oxalate solution. Okay. All right, now, first let's identify what you're looking for. If you remember, concentration is molarity, and molarity of what? The oxalate. We don't have just an oxalate by itself, but if you look, we have sodium oxalate, and you should notice this is a strong electrolyte because it is bonded with sodium, which dissociates completely in water. So sodium, there are two NAs, and if it's called sodium oxalate, sodium is the cation, oxalate is your anion. So you're looking for the molarity of this guy right here, C2O4 2-. All right, so in order to figure that out, we are going to use the information that we're given. We said that we are at equivalence point at 14.56 milliliters of potassium permanganate added. Well, let's use the molarity formula to figure out how many moles of potassium permanganate we actually added. So we're going to use the molarity formula. Molarity is equal to moles over liters. The potassium permanganate was 135 molarity. We don't know moles. We have the volume added, which is 0.01456 liters. And then we just multiply the two values together, and that will give you the moles. So 0.135 times 0.014566. That means that we added 0.00, and I'm going to round this up to 2 moles of KMnO4. This is how much we added. All right, and we got that number by multiplying the molarity 0.135 and the volume 0.01456. All right, and now what we want to do is we want to figure out the moles, because we have moles of KMnO4, but we don't want KMnO4. We want molarity of oxalate. So we want to figure out how many moles of KMnO4 there are per moles of oxalate, C2O4 2-. Okay, now, so to do that, we need to have the full equation. Okay, unfortunately, we don't have the full equation. We only have the half reactions. Right, we have this, the reduction half reaction, and the oxidation half reaction. And so we need to combine them using Hess's law. However, if you notice, if you take a look at the electrons, here we have 5 electrons, and here we have 2 electrons. We need to balance that out. So in order to balance out these formulas, we need to multiply everything, or we need to multiply the reduction by 2 and the oxidation by 5. That way the electrons can cancel out. So we're going to take the reduction reaction, and we're going to multiply that by 2. That will give us 16H plus 2 MnO4 minus plus 10 electrons produces 2 Mn2 plus 8 H2O liquid. And then for the oxidation, we're going to multiply that by 5. That way we can cancel out the 10 electrons. So 5 C2O4 2-, 10 CO2 plus 10 electrons. And so the 10 electrons will cancel out, and then we can combine this to get our reaction. But I don't need to write the reaction because I just need to know the ratio between oxalate and potassium permanganate. So oxalate, if you take a look at our reaction right here, has a coefficient of 5, so it'll be 5 right here. There's no potassium permanganate, but if you take a look, we have manganate. And there's 1 manganate in every potassium permanganate, so it'll be 2. So 5 over 2. All right, and if you use dimensional analysis to simplify this, you should get 0.005 moles of C2O4 2-, And we're not looking for moles, we're looking for molarity, and we know that molarity is moles divided by liters. So we take the moles divided by the volume that we had originally, which is going to be 0.05 liters. And so we end up with a molarity of 0.01 molarity C2O4 2-. Okay. So that's how we can combine all this molarity, the molarity stuff that we have learned in the past, with the new half reaction things. Basically, you just need to make sure the electrons are equal so they can cancel each other out on the reactant and product side, and that will allow you to get the ratio of whatever compound you're looking for in the reaction. All right, so let us move on now. Okay, so we're going to take a look at something new called reduction potentials. And reduction potentials are where we start actually talking about electricity now. Okay, so every half reaction has an electric potential or voltage associated with it. And what voltage pretty much is basically the energy that is produced by the electrons moving in the reaction. So when we have a half reaction like this, just like enthalpy, we have an electrical potential associated with it. So this would be the reaction, and this would be the reduction potential that is associated with it. Now, the key thing to note is that whenever you are given an electrical potential and a half reaction, it is always written in the form of a reduction reaction. Okay, you are not going to be given an oxidation half reaction and an electrical potential. It will always be given to you in reduction. So you want to double check and make sure the electrons are on the reactant side. So, for example, this is our reaction right here. Zinc is combining with 2 electrons to become solid zinc, and this is the reduction potential right here, negative 0.76. Now, if you want to flip it to get the oxidation one, it's very simple. It's just like enthalpy. When you flip the reaction, the electrical potential becomes the opposite sign, so it goes from negative to positive. All right, now let's talk about what these numbers mean. The bigger the number, the more likely it is to occur. So the bigger the electrical potential, the bigger the number, and by bigger, it's not just magnitude, it's talking about how positive it is. So the more positive the number is, the more likely it is to happen. So this reaction right here has a very big reduction potential, positive 2.87. So this reaction is more likely to happen than this one, and definitely more than this one right here. If you actually have a negative reduction potential, you actually need an input. We need to put energy into it for this reaction to take place. Okay, and then we got another example right here. If you take a look right here, this is lithium's reduction. This is lithium's oxidation. And if you look at the oxidation, it's a positive number, and the reduction is a negative number. That means that the oxidation of lithium is more likely to happen than the reduction, because this value is positive, whereas this one is negative. In order for this to happen, you actually need to put energy into the system in order to make it happen. All right, so we got this problem right here. And what we're going to do is we're going to we're going to calculate the electrical potential of this full reaction, this one right here, using these 2 half reactions. So in order to do that, we're going to pretty much just use Hess's law to make this reaction using these 2 half reactions. So let's take a look at the reaction that we want to make. If you take a look, F2 is on the reactant side. So we look for the reaction with F2. F2 is right here. Perfect. F2 is on the reactant side, so we can just copy down what we got. So F2 plus 2 electrons produces 2 F minus, and the electrical potential is positive 2.87 volts. Next compound is Li. And if you take a look at Li, solid, it is on the product side of this one. So we actually need to flip this equation right here. So we're going to flip it so that we get lithium on the reactant side, Li plus on the product side, and an electron. And since we flipped it, the electrical potential needs to become a positive number. However, we're not done yet, because if you notice, we need to cancel out 2 electrons right here, right? So what we need to do is we actually need to multiply this reaction by 2 to get 2 Li, 2 Li plus, and 2 electrons. And this is where electrical potentials are a little bit different from enthalpy. Okay, if you guys remember, in enthalpy, when you flip the reaction, you change the sign, right, from positive to negative and vice versa, which we did right here. But if you double the reaction, we used to have to multiply it by 2. However, when it comes to reduction potential, and I want you guys to write this down, do not multiply this number. Okay, even if you multiply it by 2, whether you multiply it by 10, doesn't matter. The electrical potential will stay the same, even if you multiply it by a coefficient. Okay, so when we flip it, we change the sign, but we do not multiply it by the coefficient when we multiply a reaction. And so to find the electrical potential of this complete reaction, we just need to add them up. Oh, let's just make sure that everything's balanced though. Electrons cancel. You got F2, F2, 2Li, 2Li, 2Li plus, 2Li plus, 2F minus, 2F minus. Looks like it's good to go. So we just add them together, and so your electrical potential will be 5.92 volts. Okay, and this reaction, we're gonna say that it is spontaneous. Okay, if you remember from the previous unit, it's gonna want to happen because the electrical potential is a very positive number. All right, so key takeaways right here is to note that when you flip a reaction, you change the sign of the reduction potential. However, you do not multiply it by the coefficient. The other thing to keep in mind is that if it is a positive number, that reaction is spontaneous. It's going to want to happen. However, if it is a negative number, it is non-spontaneous. It does not want to happen. All right, so that leads us into a, I guess, type of problem that is very common on the AP test when it comes to this. And basically, this is what the problem looks like. It's going to make us predict if putting a metal in a solution containing the aqueous ions of another metal will cause a new solid metal to start forming. So if we want to visualize what that looks like, basically, let's say that you have a solution, and we'll call this metal A. Let's say that you have metal A ions inside of the solution. If you put a stick of metal B, okay, and this is going to be solid, a stick of metal B on the inside the solution, basically, will metal A start to solidify on the surface of metal B? Okay, that's a type of question that's very common when it comes to reduction potentials, and I'm going to show you guys how to solve that type of problem. Okay. All right, so we have this information right here, but before we look at it, let's just look at the problem and figure out what it's asking us to find. Okay, so part A is asking, will placing solid zinc in a solution containing Ag plus ions produce solid Ag? And then you want to justify. So before we start, I'm going to color code this for you. I am going to color code zinc as red, and we're going to color code Ag as blue, just so that we can visualize it a little better. So what the question is asking us is, if I have a solution and I have Ag plus ions in there. So I got Ag plus, and it's an ion, so it's aqueous. If you got Ag plus ions floating in there, and you put a piece of solid zinc inside of this solution, so solid zinc, is Ag plus going to start forming on the surface of the zinc? Now, if we take a look at this reaction right here, we can see how that happens. Ag can turn into Ag plus, so this can turn into Ag plus if it can gain an electron. So basically, if Ag plus can steal an electron from zinc, that means it will start to steal electrons and form Ag solid on the surface of the metal. Okay? So the question is asking, is this going to happen? So in order to solve that, we need to look at the reduction potentials, because if you remember, reduction potentials tell you if a reaction is spontaneous or not. Is it likely to happen? So that's going to actually tell us, is it likely for Ag to take electrons from zinc? All right, so in order to do that, we actually need to figure out if this is able to happen. So let's take a look at this reaction right here. Ag plus turning into Ag solid. This is going to be reduction, right? This is the one that we're trying to look at if this is possible. So we're going to call this reduction. Sorry, let me write it right here. So basically, the question is asking, is the reduction of Ag plus going to happen? Okay, now, if Ag plus is being reduced, I'm going to write down the half reaction. Reduced is gaining electrons, so Ag plus gains an electron to form Ag solid. Ag is going to get the electron from zinc. So if Ag is reduced, zinc is being oxidized. And if you oxidize, remember, electrons are going to be the product, so we got to flip this reaction right here. So zinc 2 plus 2 electrons. All right, so we're going to take a look at the electrical potentials of these two half reactions. The reduction of Ag, the reduction potential is plus 0.8 volts. And for zinc, zinc is being oxidized. So what we need to do here is we need to flip it. So the reduction potential will be positive 0.76 volts. Okay, we're going to double this so that the electrons can cancel out. And then we're going to figure out if this is going to happen. If you add up the electrical potentials, you should get positive 1.56 volts. And if you remember, if you have a positive electrical potential, that means that this is a spontaneous reaction. It wants to happen. So in this situation, the answer for part A, the answer is yes. Placing solid zinc in Ag plus solution produces solid Ag, and then you would write something along the lines of because we would say the electrical potential is positive, this reaction is spontaneous. It wants to happen. All right, so basically, because the electrical potential is a positive number, positive 1.56, that means this reaction is going to happen. Ag plus is going to take electrons from zinc to form solid Ag. All right, I want you guys to pause the video and try part B. This is going to be the opposite. Will placing solid Ag in a solution containing zinc 2 plus produce solid zinc? So just the reverse. Let's say that we have a solution. If you have zinc ions inside of it, and you put a piece of solid Ag inside of it, okay, will the zinc ions take electrons to form zinc solid on the surface? Will this happen? Okay, I want you guys to pause the video, see if you can figure it out, and write your explanation as well. All right, everyone, welcome back. Let's see if you got this correct. So what you're going to do first is you're going to take a look at the half reactions and figure out which one you want to flip and which one you want to keep as reduction. So we're going to take a look at our half reaction. So we're going to see if zinc can turn into solid zinc. So we're going to take a look here, and zinc turning into solid zinc is going to be this first one right here. So basically, we're looking at, is zinc going to become reduced? So we're going to write down this reaction right here. Zinc 2 plus gaining 2 electrons to form zinc solid. Now, if zinc is being reduced in the situation, that means that Ag needs to be oxidized. So we've got to flip it to Ag solid, forming Ag plus and E minus. We're going to balance that out. So 2 and 2, so that these cancel. Now, for the reduction of zinc, we already have the electrical potential right here. The electrical potential is negative 0.76 volts. Ag is being oxidized, so what we're going to do is actually flip this because we flipped the reaction. So this is going to be negative 0.8 volts. And if you look at the electrical potential this time, now it is negative 1.56. And remember, if you have a negative electrical potential, this is non-spontaneous. It does not want to happen. So what you would want to write is that the answer is no. Putting solid Ag in zinc does not produce solid zinc because the electrical potential of this reaction is negative. It is non-spontaneous. Zinc is not able to take electrons from Ag because the electrical potential becomes a negative number. All right, so that's the type of question you might have when it comes to comparing electrical potential. Okay, whether or not putting a metal inside a different metal solution will form a solid. All right, everybody. So now that we have talked about electrical potentials, we can start getting into the, I guess, big topic of this unit, and it's going to be something called a galvanic cell. So we're going to take a look at what a galvanic cell is. I'm going to draw it out for you because there are a couple components to it, actually a lot of components to it, and you need to know what all of them do, unfortunately. So we're going to go through it step by step. Okay, so what we're looking at is called a galvanic cell. All right, so a galvanic cell, and if you are old, you might call it a voltaic cell. So if you see voltaic cell, just know that it's the same thing as a galvanic cell. Basically, what a galvanic cell does is it uses a thermodynamically favored reaction. So basically, it is spontaneous, which we just learned means the electrical potential should be a positive number. Okay, so it uses a thermodynamically favored reaction basically to generate a flow of electrons. So basically, you use a spontaneous reaction to make electrons move, and that creates a current. Okay, it basically makes electricity. If you ever watch Breaking Bad, there's actually a very famous scene where Jesse and Walter White are stuck out in the desert and the RV runs out of electricity. So Walter White uses chemicals to make a battery to recharge the RV. And what he basically made was a galvanic cell. You use a spontaneous reaction to make electrons flow, and so you can make a current. All right, so we're going to take a look at a galvanic cell because it's a very big part of the unit. They like to ask a lot of questions about it. So I'm going to show you guys how to analyze one and how we can answer a couple questions about them. Okay, so there are a couple components to a galvanic cell. First, there are two different containers. Okay. There are two different containers, and they have a solution inside of it. Now, one of the sides, or excuse me, both of them have a solid piece of metal inside of it. Okay, so they're both going to have a solid piece of metal. Okay, now the two pieces of metal will be connected with a wire. All right, so one of the metals one of these containers is going to be called the anode, and the other container is going to be called the cathode. Okay, now, in the anode, this is where oxidation takes place. And in the cathode, this is where reduction takes place. Okay, so the metal here is going to lose electrons. The metal here is going to gain electrons. So basically what's going to happen is the electrons are going to move from the anode into the cathode, right? Because electrons leave, the anode loses electrons, it's oxidized. Remember oil rig? Oxidation is loss of electrons, and cathode is reduced, so it gains electrons. Okay? All right, now let's talk about what the anode and the cathode are. Basically, they're two different metals. So I'm going to call it metal A and metal B. So this stick is made of metal A, solid metal A, and this stick will be made of solid metal B. Okay, and inside of this solution is going to be metal A ions. Okay, and in this solution, there's going to be something called, there's going to be metal B ions. Okay, and they're both metal, so they'll both be cations. And typically, there will be another anion inside of it, something like NO3-, right? Something that's going to just stay dissociated. And that's just manually to balance out the positive negative energy of the ionic compound. But this doesn't really matter. What really matters is that the cation is the same as the metal. All right, now basically what's going to happen is there's going to be an oxidation reaction here, and there's going to be a reduction reaction. So let's talk about what that means. Remember, oxidation is loss. So what's going to happen is this metal right here is going to lose electrons. So in this piece of metal, in the anode, this solid piece of A has electrons, right? Every element has electrons, and electrons are going to leave this piece of metal. So the solid metal is going to lose electrons, and if I lose electrons from solid metal, if I lose electrons, I become positive, right? So metal A is going to become positive, and what's going to happen is it's going to start dissociating into the solution. So electrons are going to leave, and because I'm losing electrons, this metal A is going to start dissolving into the solution. So what's going to happen is this metal right here is actually going to become smaller as time goes on, because electrons will leave, excuse me, and the solid piece of metal will dissolve. On the other hand, right here, reduction is taking place. So electrons are going into this piece of metal, and what's going to happen is the ions inside of the solution are gonna start getting attracted to the electrons that are inside of the electrons coming into this metal, and it's gonna start forming this layer of solid metal B on the surface of the cathode. Okay, so metal B is gonna get reduced or gain electrons, and it's gonna form a solid metal on top. So this metal piece right here is actually going to get bigger over time. Okay, and that's actually the main parts of a galvanic cell. There's one thing that we haven't gone over, but if we just think about the gist of it, there's an anode and cathode. In the anode, oxidation takes place. So the anode is going to lose electrons. If it loses electrons, it's going to become, the electrons are going to leave it, and as it leaves, the solid metal starts to dissolve into the solution. And then as the electrons leave and go to the cathode is going to become bigger because it is gaining electrons, so the ions inside of the cathode are going to become attracted to and form solid. So this piece gets smaller, this piece gets bigger. And I have a picture right here on your workbook, and this is an example of an actual anode and cathode. The anode, if you guys notice, is getting smaller, and the cathode is getting bigger because solidifying. So here's another chart if you want to take a look at it. But there is one other thing that we need to talk about. It's a very important component, and it's something that completes the circuit. You might have learned in previous science classes that electricity needs to form a circuit. It needs to form a loop. It can't just be one way. And the thing that completes the circuit is this thing called a salt bridge. All right, and the salt bridge is typically made out of a strong electrolyte, so something like KCl. And what this does, it's going to basically balance out what's happening in the galvanic cell. So if you take a look at the anode, you guys can see that it's going to become really positive inside of the solution, right? Because the solid metal is going to turn into a cation and dissolve. So to balance out all that positive energy, KCl, the salt bridge, is made out of a strong electrolyte, which obviously is made out of these things right here. So K plus and Cl minus. And what's going to happen is, since this side gets really, really positive, to balance that out, all the Cls, or the Cls inside the salt bridge, are going to start going into this solution right here to keep the positive negative energy balanced out. Okay, so because it gets more positive because of the cations associating, the Cl is going to dissolve into the anode. And on the other side, if you guys notice, the metal ion inside the solution becomes a solid. So this side is going to start losing positive energy. It's going to become too negative. So to balance that out, the positive cation in the salt bridge is going to dissolve into the cathode. So the salt bridge is actually going to dissolve over time as well, because the anion of the salt bridge is going to go into the anode to balance out all the positive energy coming in, and the cation is going to dissolve into the cathode to balance out all of the cations becoming solid. So that is a galvanic cell. I know there were a lot of components. You might have missed some of it. I would recommend going back and re-watching this a couple times to make sure you can pick up all the different components of it. But we're going to go over 2 galvanic cell problems just to make sure that we got this really dialed in. Okay? But I would really recommend going through this multiple times just so that you understand every component of the galvanic cell, because it is really important for this unit. It's going to be on your exam 100%. So you really want to understand this. All right, so if you've gone back and watched it a couple times and you understand galvanic cells, hopefully that got you ready for the galvanic cell problems that we're going to go over. Okay, so 14.7. Here we have a galvanic cell, and it's made out of tin and copper. And as current flows through the cell, it says that the student can see that the copper has increased in mass and the tin has decreased in mass. And just based on this information, we need to solve the rest of the problem. Okay? Alrighty, so let's go over all the parts. Now, hopefully if you understand galvanic cells, you should be able to do this problem without your notes. The first time, maybe I'd say it's okay to look back at your notes just to remind yourself of this, because this is such a not complicated, but there's a lot of components to a galvanic cell. But eventually, you should be able to answer these problems without your notes to get ready for the exam. So just want to give you a heads up. First try, be able to do this with your notes, but afterwards, see if you can do it without your notes, okay? All right, so part 8. It asks which electrode is oxidation taking place and which electrode is reduction taking place. So we got oxidation and we got reduction. Now, I'm going to teach you guys an acronym that's going to be very helpful for these galvanic cells, and it's going to be this acronym right here. It's going to be red cat and an-ox. Okay, red cat and ox. What does that mean? It means that reduction, happens at the cathode, and at the anode, there is oxidation. Okay, red cat and ox. This will help you keep everything in mind. So, using that acronym, oxidation is going to happen at the anode, and reduction is going to take place at the cathode. Now, I do want to warn you, never memorize a galvanic cell based on left and right, because it will switch based on the problem. And so you really want to identify what the anode and cathode are. Okay, so to solve this part, we need to look at the information that is given in the problem. It says that the copper increases in mass and the tin decreases in mass. So what we can see from that is that copper right here is increasing in mass. If it is increasing in mass, that means the copper that is in this solution is starting to form a solid on the surface of the copper metal stick that's inside of it. Okay, because it's increasing in mass. That means it is solidifying. The copper 2 plus is turning into Cu solid. So what we can see here, based on this information, is the copper ion, the aqueous copper, is turning into solid copper. Now we're going from a positive cation to a neutral metal, so we got to figure out, did it gain or lose electrons? Well, you're going from positive 2 to 0. And if you're going from positive 2 to 0, that means you are gaining electrons, right? Because if you have a number scale, 0 and positive 2, if you're going from positive 2 to 0, you're becoming more negative. If you are becoming more negative, that means you are gaining electrons. So here, you are gaining electrons. And if you remember oil rig, if you gain electrons, right, reduction is gain. So copper is being reduced. Okay, so copper is being reduced. That's the information that we can get out of this. So that means that at which electrode is reduction taking place is going to be at the cathode, and the cathode is going to be copper. Okay, and you can check back your notes. You should see that the cathode is the one that gets bigger. Okay, you can also get the same information using the one with the tin. If you look, the tin is decreasing in mass. That means it's getting smaller. That means the solid tin is starting to dissolve into the solution. So Sn solid is becoming Sn2 plus aqueous. All right, so if we see that you're going from 0 to positive 2, that means you're becoming more positive. That means you are losing electrons. So here, electrons are a product. Okay, and if you remember oil rig, oxidation is lost. Tin is losing electrons to become the cation in the solution. That means that tin is losing electrons. That means that tin is being oxidized. So that means that oxidation takes place at the anode, and the anode is going to be tin. Okay, and that's actually going to answer A and B. The cathode is going to be copper, and the anode is going to be tin. So we would use this information about one of them getting bigger, one of them getting smaller to figure out what the cathode, the anode is, and which one is being oxidized and reduced. All right, part C. This one's a general piece of information you're going to need to know. As tin decreases, as the mass decreases, where's the mass going? Well, we know from our knowledge of galvanic cells that the solid tin becomes aqueous. So you would say something along the lines of tin solid ionizes into solution as, I apologize for my handwriting, as tin 2 plus, and then you would write aqueous or ions. Okay, and then you say something along the lines of, that's why the solid mass gets smaller, because the solid tin becomes aqueous tin. It dissolves into solution. Part D, what's happening at a molecular level at the salt bridge? Salt bridge is made out of KCl. How are the molecules that make up the salt bridge moving? Well, the salt bridge is made of KCl. We know that KCl is K plus and Cl minus. And if we take a look right here, if tin dissolves, it makes more of these cations in there. It's becoming very positive because it is ionizing into Sn2 plus. Well, if it's becoming very positive, we want to balance that out. So we're going to balance that out by having this in the salt bridge. Cl minus is going to dissolve into the into this solution right here in order to keep the positive and negative energy balanced out. So you would say on a molecular level as a salt bridge, Cl minus dissolves into, and then the Sn is the anode, into the anode. And then the opposite is true on the other end. If this copper is turning into solid, you are losing cation in the solution, so it's losing its positive energy. So to keep it balanced, the K plus is going to dissolve into it. And then you would write something along the lines of K plus dissolves into the cathode. All right, and then last question, which way is the current moving? If you remember, you can memorize it a couple ways. You can remember that current always goes from the anode to the cathode, but I like to just look at the equation. If you take a look at this half reaction right here, Sn is losing electrons as it ionizes, right? So it turns into Sn2+, it ionizes here, and the electrons leave the tin and go to the copper. So you would write, you can either draw it, I guess. You can, if it asks you to draw, you can draw it like that. Or you can say the current is moving from the Sn anode to the Cu cathode. All right, and that is a galvanic cell problem. Again, it's all interconnected, and it really shows if you understand the different components. There are a lot of different components to a galvanic cell problem. And so that's the reason why I really recommend going back and looking through it a couple times. Also, if you scroll down a little bit, you will see I wrote a pretty comprehensive explanation of all the things that happen in a galvanic cell. So if you like a written medium a little bit better, you can read through this while looking at the image, and that will allow you to get some more information and explanation on the galvanic cells. Okay, so with that being said, and without promoting what I wrote, to get some credit for it, I want you to pause the video and try this problem right here, 14.8. You got a galvanic cell, and it gives you this information. See if you could pause the video and try this on your own. All right, welcome back, everybody. Let's see if you guys got this correct. So let's go through. Let's go through this problem. So it gives you this reaction right here. It's telling you that this is a reaction that takes place in this galvanic cell. And it gives you this image, but it doesn't tell you where each metal is. It just tells you the current goes from left to right, from X to Y. And then the first problem is asking what is Y and Y2+. So we need to figure out what is happening. First thing we're going to do is take a look at the reaction and figure out what is being oxidized and what is being reduced. So if you did not try this out, pause the video and see if you can figure that out at least. But if you have, you can see that CD goes from 0 to 2+. It is becoming more positive. That means it is becoming oxidized. Which means that PB, as it goes from 2+ to 0, is being reduced. All right, oxidation and reduction. Now, if you remember oil rig, again, these acronyms help quite a bit. Oxidation is loss, reduction is gain. We can see that electrons are going from X to Y. That means X is losing electrons. That means here, where X is, this is where oxidation is taking place. Y is gaining electrons, so reduction is gain. This side is reduction. So Y is being reduced, X is being oxidized. So if you take a look at Y is being reduced. Let's look at what's happening here. PB2+ is reducing to PB solid. So that gives us our answer. Our answer for part A is Y is PB solid, and Y2+ is PB2+ aqueous. And we can see that because electrons leave X to go to Y. That means Y is gaining electrons. Reduction is gain. PB is being reduced, so that's how we got this information right here. All right, for part B, this one actually required you to do your reading. I didn't mention it in this video yet, but I'm going to tell you guys just the answer. What's the initial concentration of this in this solution? Well, if you take a look at this problem, it says it contains 2 standard cells, 2 standard half cells. Okay, if you guys did your reading, you would know that standard half cells are 1 molarity. So that's going to be your answer, 1 molarity. So be very astute about what the question is saying. It says that the galvanic cell is 2 standard half cells. Half cells are, or excuse me, standard half cells are always 1 molarity. All right, part C. What is the cathode? What is the anode? Well, if you guys remember the acronym I just told you, red cat and anox. Okay, reduction is the cathode. So if we take a look right here, Y is being reduced and reduction is cathode. So that means the cathode is where reduction takes place. And what is being reduced? Pb. Or in this case, Y. Y is being reduced. Okay, so the cathode is where reduction takes place. So reduction. And reduction is going to be Pb. You can also say that it is Y. And then anode, anox. Anode is where oxidation takes place. And if you take a look right here, oxidation happens to cadmium, which is also known as chemical X in this problem. So any of those answers work. All right, part D, we want to write the balanced equation. So for this one, we have the electrical potentials. And so we want to just write down what's happening at the cathode and the anode. So we know the cathode is going to be where reduction takes place. So that's going to be where chemical Y is. We just established that chemical Y is Pb. Okay, so Pb. And then the oxidation takes place at the anode. And that's going to be for cadmium. Now, the key thing to remember here is that half reactions, you might want to jot this down if you forgot, half reactions are always given in reduction. So they are given in reduction. Okay, so that means that for both of these, we need to make sure that we are writing it in terms of reduction. So reduction is gaining electrons. So we're going to be talking about how they gain electrons. So for Pb2+, let's start with that. Pb2+ can gain 2 electrons to become Pb solid. Okay, because it's gaining. Cd2+ can also gain 2 electrons to become Cd solid. And these are their electrical potentials. However, if you take a look up here, we can see that Cd is being oxidized and Pb is being reduced. So we have to make sure that they are, even though they're both given in reduction right here, for the oxidized one, we need to flip it. That means that this half reaction right here, we're going to flip it to Cd solid, become Cd2+ and 2E-, which is the form that we have right here. Cd solid on the reactant side, Cd2+ on the product side. And then if we do that, the electrical potential is going to flip signs, so from negative to positive, 0.4 volts. Okay, the electrons will cancel out, and then we can combine it. On the reactant side, we're going to have Pb2+ and Cd solid. It's pretty much just this reaction right here. So Cd solid plus Pb2+ produces on the product side Cd2+ plus Pb solid right here. All right, and then for last one, part E, we're going to use what we just did. At the cathode reduction, we have negative 0.13 volts plus at the anode where oxidation takes place, we have 0.4 volts. Okay, we just need to combine them together, and that will give us positive 0.27 volts. And that'll be our answer. Now, one way you can always check your answer for these problems is that for galvanic cells, if you remember, very beginning of when we started talking about this, galvanic cells are always spontaneous. They're thermodynamically favored, which means that the reduction potential has to be a positive number. So if you get a negative number for the electrical potential of a galvanic cell, you know that you messed up. because galvanic cells, by definition, have to be a positive reduction potential. They have to be spontaneous. Alrighty, guys. So that is galvanic cells. Now we're going to move on to the other type of cell that is talked about in this unit. It's not as common, but there are a lot of questions about this type of cell as well. Alright, so the other type of cell that we're going to talk about are called electrolytic cells. And if you remember galvanic cells, okay, they were thermodynamically favored. So they were thermodynamically favored reactions. They were spontaneous, which meant that the electrical potential is a positive number. Electrolytic cells are different. You also see them when the questions refer to them as electrolysis. They are thermodynamically unfavored. That means they are non-spontaneous. And that means for electrolytic cells, the reduction potential has to be a negative number. This is the key difference between the two. Galvanic cells, the electrical potential is positive. Electrolytic cells, electrical potential is negative. So the difference is galvanic cells, they happen on their own. That's why Walter White could make this in the middle of a desert. He could just make the chemicals react because the electrons moved on their own. He didn't need to put in any energy. But for electrolytic cells, it's negative. So you have to put in energy to make this happen. And reduction potential is negative. Alright, so a couple things about electrolytic cells. Most electrolytic cells, they happen in aqueous solutions, which are created when a chemical dissolves in water. And basically what happens is either the ions that are dissolved in the water or the water molecules themselves can be reduced or oxidized. A couple things to note is since electricity is provided, we want two half reactions that we're combining to be as close to zero as possible. So when we are looking at an electrolytic cell, when you add the reduction potentials together, you want it to be negative, but you also want it to be as close to zero as possible. Okay, that's what this means right here. Another difference is in a galvanic cell, remember how the anode and the cathode changed mass, right? One of them dissolved and one of them got bigger. Well, in an electrolytic cell, they just sit there and they conduct the electricity, but they do not take part in the reaction. So the anode and cathode in an electrolytic cell do not change in mass. One doesn't get bigger and one doesn't get smaller. All right, so I'm going to draw one for you just so that you guys have an idea of what's happening. But here, we're going to draw an electrolytic cell, and here it says that we have a solution of nickel 2 chloride, and in this solution there are Ni2 plus ions. So in the solution we'll have Ni2 plus ions, Cl minus ions, so that means they're aqueous. And since it's aqueous, there's also water, H2O liquid. All right, now for an electrolytic cell, you're going to have your cathode and you're going to have your anode. Okay, and they are going to help facilitate the movement of the electrons, but since this is thermodynamically unfavored, there's going to be a battery. Okay, electricity needs to be put in. Okay, now the cathode for electrolytic cell is going to be the negatively charged one, and the anode is going to be the positively charged one. All right, so we have three different chemicals, three different compounds that are involved: nickel, chloride, and water. Now there are four possible half reactions. First, since nickel is positive, right? It's a positive ion. It can be reduced. It could gain electrons to become Ni solid. That's one possibility. The other possibility is Cl minus is negative. So it can be oxidized. So that means it could lose an electron and it could become Cl2 gas. So in an electrolytic cell, typically a gas will be formed and it'll lose 2 electrons because there will be 2 of them. Okay, the other thing that can happen is the water itself can be oxidized or reduced. So water can be oxidized or reduced. So there are two options for water. And these are the four possible reactions that can take place in an electrolytic cell like this. Okay, so those are the four possibilities. And if you scroll down a little bit, you can see what the four possibilities are and their electrical potentials. Now, you do not need to memorize these. They will always be given to you. So typically, what happens in these electrolytic cell problems is they will give you these four reactions, and they'll basically ask, what are the two half reactions that are most likely to take place? And you'll need to figure that out. And then they'll ask you, write the actual reaction that happens and its electrical potential. All right, so let's talk about how to figure that out. So we're going to use this as our first example, and I have some tips for you right here. So for an electrolytic cell, remember, the reduction potential has to be negative. So when we're basically going to pick two of these. One of them is going to be oxidation, one of them is going to be reduction, and when you add them together, it needs to be negative. Second, it needs to be as close to zero as possible. And so that will actually, these two things are going to control what we pick. Now, if you remember, all of these are given in terms of reduction. So the one of them, we need to flip it into oxidation. All right, so let's figure out what we need to pick. The first thing we're going to pick is we're going to pick the one that is reduced. So we want to make sure that this number is negative. And so we want to pick the nickel. This one right here is going to be your reduction. So we want to pick this one as your reduction because we want it to be negative, but we also want it to be as close to zero as possible. And this is the smallest in terms of magnitude for your reduction. So this is our reduction reaction. Ni2 plus 2 electrons produces solid nickel. And the electrical potential is negative 0.25 volts. All right, so we picked our reduction potential. We picked nickel because it's the smallest negative. Remember, electrolytic cells need to be negative. So we picked the smallest negative number. And then we're going to pick our oxidation. Now, if you remember, we have to flip the one that we picked for oxidation. So let's just look at this. If we flip this one, it will become negative 1.23. This will become negative, and this will become positive. So we can automatically see we will not pick this one because if we flip this one as oxidation, that means that this becomes a positive number. If we add 0.83 and negative 2.5, that's going to give us a positive number. Electrolytic cells need to be negative, so this is not an option. And then between the two, we want to make sure that the reduction potential is as close to zero as possible. And so we're going to pick this one right here as our oxidation. Okay, we want to flip this. That way we can make it negative, and that'll get us close to as zero as possible. If we pick this one, it would become a number that is more negative than if we pick this one. So we're going to flip this one. So it'll be 2H2O, O2 gas, plus 4H plus 4 electrons, and we flip it so that E is equal to negative 1.23 volts. All right, so to get our balanced equation, what we got to do is we got to cancel out the electrons. There's 2 and 4 here, so we got to double this one. So it'll be 2, 4, 2. But that does not mean we change the reduction potential. Remember, we don't multiply it by the coefficients. We do that, the electrons will cancel out. And then we use Hess's law to combine it together. So the balanced equation in this electrolytic cell will be 2Ni2 plus 2H2O liquids produces 2Ni solids plus O2 gas plus 4H plus. And then for the electrical potential, you just add them together. So E is equal to negative 0.25 plus negative 1.23. And that is going to give you negative 1.48 volts. And that will be the reduction potential of your electrolytic cell. All right, so if we're to visualize what's happening inside of this electrolytic cell, let's go back to our original drawing of what the electrolytic cell has. So we're going to have our container. We have our cathode. We have our anode. And then we have a battery. And here we have Ni2 plus ions, Cl minus ions, and we have water. So if we take a look at the information that we got from the balanced equation, this is what's happening. Ni2 plus is becoming solid Ni. And if you look at it, in order to go from positive 2 to S, from aqueous to solid, we go from positive 2 to 0. So here, this is being reduced. Okay, so solid nickel is going to start getting formed at the cathode. So at the cathode, we're going to have nickel being formed. So here, the Ni2 aqueous is going to become Ni solid right here. So this will be Ni solid. So that's what's happening at the cathode. And then at the anode, we can see that H2O liquid is turning into O2 gas and H+. So what's going to happen at the anode is H2O is going to go at the anode, and then it's going to be oxidized. It's going to lose electrons. And then what's going to happen is it's going to form O2 gas. So it's going to form a gas, and it's going to pretty much bubble out. And then you'll also form H+. So this is where the reduction takes place, and this is where the oxidation takes place. Okay, so that is what is happening in an electrolytic cell.